is recording it. Section 2.4. You guys will actually like section 2.4. By the way, there's no quiz today if you haven't figured it out. There weren't any theorems or definitions in the section, so no quiz today. And I forgot to put the P in, skip the last example. When you're outlining next time, we're going to have outline on section 3.1. So make sure that you skip that last example for Thursday. Yeah. So do everything through the end of the proof of 3.1.3. Then that last example is like a page or a page and a half thereabouts. You're going to skip that last example on it. We're not going to cover that. And that is going to be due at the start of class on Thursday. And then also due on Thursday is the homework for 2.4.
So this is the test. Is one chapter 2?
Yeah. We're only covering, I think, 2 sections in chapter 3.
Oh.
Mm-hmm. So yeah, if you look and see when the next test is. Yeah. I chose it to be on a Tuesday. Try and keep it on a Tuesday so you guys have the greatest amount of time to study for over the weekend, rather than review on Tuesday, test on Thursday. So this one will just be through chapter 2, and the next test won't include anything from chapter 4.
I have a question. On your outline, like if on like page 142 or like
Mhm.
we have 1.3, like when we outline those groups, how
Mhm.
are we supposed to write that?
Okay, so you give me a step for each line after the if and only if. So if they have more than one if and only if on a line, then you give me a step for each of those. So tell me what they're applying to get from one if and only if condition to another. And it's usually a previous theorem statement.
It's like from the theorem. So like
Yeah.
if we have the theorem 2.1.3, like the first thing, I don't know. But
The
would be
first thing's
A.
your hypothesis.
Yeah, it would be hypothesis, and then
And then after the if and only if, they're applying the definition for what it means to be in your function composition.
which is the A of theorem.
No, that's actually definition for function composition. So if you go back, you have the definition on the top of page 141
Oh, so we need the definition of composite.
of a composite function. Mhm. And then they apply it again inside. And then they're going to redistribute the and stuff like that. So you're going to tell me each step what they did to get to the next step. Okay, so section 2.4. I can actually finally give you steps to a proof. Corday, I gave homework out to everybody before class, before we did the reading.
I'm gonna give you yours before I forget.
Okay, we have a principle of mathematical induction. Your book in section 2.4 did not call this a theorem. I am calling it a theorem, and we're going to actually prove that it works. So this is, if you're following along in your book, we're starting on page 100. Did I give you an extra paper? Sorry. Mathematical induction says, let S be a subset of the naturals with these two properties. One is in S, and for all n in S, for all n in the naturals, if n is in S, then n plus 1 is in S. And then we say that S is equal to the natural numbers. Based on these two properties, you can show that S equals the natural numbers. Notice that the second one right here, this is called the inductive property. So, what's the hypothesis? Everything before then, right? I'm trying
N
to,
plus one is a.
no, I get to assume everything up until the then. So I assume everything before the then, and then what's after the then is what I'm trying to show. So the hypothesis is going to be, let S be a bounded set contained in the naturals with property 1 and property 2 holding. So those are my two properties. I want to show that S equals to the naturals. How do you show equality of two sets? Spring break did it to us.
Is that union?
It's subsets.
Yeah, okay.
Yeah. So what do I know? By hypothesis, well, what do I know? That's a tricky question.
I have a question.
What's your
Are you
question?
proving that they are right now?
By hypothesis, I know that S is a subset of the naturals. That's our hypothesis statement right there. So we have to show just the other direction, that the naturals is a subset of S. How do you show a subset? We had a term for it, we called it element chasing. Remember that term? Element chasing. You start with something in the naturals, you show that it lives in S. So let X be in the naturals. Actually, I want it to be like, feel like a number, so I'm going to say let N be in the naturals. We already have N's written down. How about a capital N? There we go. Now it looks different from the other N's that we have there. Let N be in the naturals. We're going to show that that N lives in S. And I'm going to actually do this proof because I don't know any information about this. I don't know anything. I don't know if N is 1 or not. So we're going to look at cases. What question?
This is what S be an odd set or
Bounded set.
bounded, okay.
That's a B. Bounded set.
Bounded set. And
Mhm.
is that the same S's?
Those are the same S's.
And why do we have to show? Always do-
If you want to show two
equal?
sets are equal, you have to show subsets both directions. Mhm.
So the let N be an N is just start off.
Yeah. Let N be in the naturals. Yes, now I'm getting ready to show that N is a subset of S. It is an element of S. So what I'm going to do is look at the case. If N is equal to 1, we're done, right? By property 1, I know N lives in S, and we're done. So let's look at the case if N is not equal to 1. By definition of the naturals, I know N has to be bigger than 1. Now, I can't apply my part 2 yet because I don't know if the integer smaller than N is in our set S. So I don't know anything about that. What we're going to do now is look at our set, our set S. We want to know that do you guys know the well ordering property? Maybe I'd just come out and say it. You guys remember the well ordering property? Okay, for the natural numbers, if you have a subset of the natural numbers that is non-empty, you're going to have the smallest element in that set. Because the natural numbers don't get any smaller than 1, so your subset either includes 1 or doesn't. If it doesn't include 1, it either includes 2 or it doesn't. At some point, you can come up to this smallest value in your set. That's our well ordering property. We're going to apply that property to S, to our set S.
So I'm saying that the smallest number in the subset of S.
Yeah.
Okay.
Yeah. So what I'm going to actually do is I'm going to assume N is not in S. Yeah, our capital N. Because I'm going to apply the well ordering property in a minute. Suppose N is not in our set S. I know 1 is in the set S, so we know S is non-empty. By the well ordering property, I know that there's a smallest element in S. I'm going to call this, I don't know, an M. So our M is the smallest element in S. Now, tell me about M minus 1. Is that bigger than M, smaller than M, or equal to M? M minus 1's a number. It's an integer.
But it's not.
You can subtract 1 from any integer and you get an integer.
But it's not in S. Because M is the smallest.
M minus 1, yes. This is less than our capital M. That's exactly what I want. I know M minus 1 is not in S. However, I know M minus 1 is in the naturals. Since I know 1 is in S.
Since you know what?
I know 1 is in S, and I know that the biggest integer, I know that the M has to be bigger than 1. M in the naturals is bigger than 1. Because we assumed that this wasn't an S. I was going to write that. M minus 1 is a natural number, since M is bigger than 1. Now, tell me about M minus 1. If I know that, I'm doing my proof backwards. You guys gonna forgive me for a second. I'm doing N plus 1. I need to be able to add 1 to that. And I know M is in S, so I want a largest integer. Let me see where I have to erase this to, and then we'll start it again. Right here. Yep, I'm doing this backwards. Forgive me, guys. right here. By the well ordering, I'm going to start it right here. So I'll let you guys erase your notes and fix it. While I erase mine and fix it, and we'll get back on the same. I need a different set. I need the complement of S. I forgot about this part. N is not in our set S, so erase it to that point right there. Now let's go and fix it. We're going to define a set P. P is going to be equal to our set N in the naturals with the property that N is not going to be in S. This is everything outside of our set S in the natural numbers. So if you look at this, you'd think of this as the naturals minus the set S. It's our set complement. Now, this value right here, the capital N, since our capital N is not in S, I know capital N has to be in our set P. Since N is not in S, N is in our set P. So I know P is not empty. It's a subset of the naturals. By the well ordering property, you can apply that to any subset of the naturals. I know that P has a least element, has a smallest element. I'm going to call that smallest element M. So I know that M is in P, and M is greater than 1 since 1 is in S. Are we good with that? 1 is in S, which means 1 can't be in P. Thus, I know that M minus 1, now that feels much better, M minus 1 is a natural number, and M minus 1 has to be, it is not in P, since M minus 1 is less than M, and M is the smallest element in P. Well, if M minus 1 is not in P, then it has to live in S. But if M minus 1 is in S, by property 2, I called it I guess. By property 2, I know that M minus 1 plus 1 has to be in S. But what is M minus 1 plus 1? You subtract 1 and add 1, what do you get? The same. So I have M is in S. Better get an extra page. And so we have M is in S and M is in P. But by definition of P is a complement of S, you have a contradiction right here. So what is our conclusion? Thus, our capital N has to be in S, because remember, all of this started by saying, suppose N is bigger than 1 and N is not in S. Thus, N is an element of S. And so I have the naturals as a subset of S. Since S is a subset of the naturals, and the naturals is a subset of S, we have that S is equal to the naturals as desired. So what does that tell us? That tells us that if we have a set with those two properties, one is in it, and it has the inductive property in it, then that set has to be equal to the natural numbers. That actually allows us to do proof by induction. Don't get too worried, you're actually going to see this proof again in just about every proof class we do. We will revisit this one. This is one that keeps coming back. Yeah, you like repetition because then it actually gets into your head. Okay, so we have a definition. A set S of natural numbers is called inductive if and only if it has the property that if n is in S, then n plus 1 is in S. So look at this example 3 here. Is that set inductive? Mm-hmm. Why is this one inductive? Because 5 says 6 is in there, 6 says 7 is in there, 7 says 8 is in there, and it keeps on going. It doesn't have to start at 1. To be inductive, it doesn't have to start at 1. Now look at example 4. Is that set inductive? No. Why? Yeah, you're missing in between integers. So that one's not inductive. You have a bunch of homework problems. They're going to ask you if it's inductive or not. It doesn't have to start at 0 to be inductive. It simply has to have every integer after its starting integer in the set. Steps for the proof by induction. There are 3 steps that you're going to be doing. The first one is to show that 1 is in S or that you have a starting spot. It doesn't have to be 1. It just has to be some starting spot. Usually it's 1, but it doesn't have to be 1 only. Once you have a starting spot, then you're going to assume that K is in S and show K plus 1 is in S. So assume K is in S, show that K plus 1 is in S. That's verifying step 2, and then this is our conclusion.
So A and B are on the steps to show how to do step 2.
Yes. Yeah, this is called the assumption step right here. So you have an assumption step, then a proof step, and then a conclusion step. So let's do some examples. Prove that for every natural number n, 1 plus 3 plus 5 up to 2n minus 1 is equal to n squared. Now I'm going to start all of these proof by induction the same way. It's a little bit different than how the book starts it, but it'll make more sense when you're typing it up. What I'm going to do is I'm going to define a statement. And I'm going to define that statement to be P of n is a statement, I use semicolon, not equals. P of n is a statement 1 plus 3 plus 5 out to 2n minus 1 is equal to n squared. That's what you're trying to verify. So you just type that down and you give it a name P of 1. You won't have to retype it all the time after that then. You just have to reference what you called your statement. So the first step, what's your question?
What is the proof you're trying to say? So are we trying to add all of our numbers to say that they equal n squared?
Up to that point right there. So if n is, say, 3, then you want 1 plus 3 plus, if you do 6 minus 1, that's going to be 5. 2 times 3 is 6 minus 1 is 5. You want to say that that is equal to 3 squared.
Okay.
For each integer, you want to be able to make that claim. Yeah, this is for all n. That's what it means for every natural number. N means for all n in the naturals. So the first thing that we're going to do is show that first that P of 1 is true. Now let's just look at this statement, P of 1. P of 1 would be what? If you plug in n equals to 1 here, you have 1. So it's 1 added up to just 1, so that's going to be 1 on that side. And what is it on the other side? 1 squared, which is also equal to 1. So that is our statement. P of 1 is that statement.
Oh, wait, would it be 1 plus 1, so it would be 2?
No. You add up to the value that you see right there.
Since it's 1.
And since it's 1, then there's no, you don't add anything else.
So if it was
Mhm.
2, we would add 1.
You'd add 1 plus, and then if you plug in 2, you'd have 4 minus 1 is 3, so you'd add 1 plus 3. Mhm. You stop at whatever value is over here. Mhm. So this statement is true. There's really no work involved in that first statement. You just have to note that it's true. So plug it in. When you're typing it up, type it up this way, P of 1 colon, and then just write in your statement, plugging in 1 for your n's. Conclude that it's true. Now we're going to do the assumption step. So assume there exists an n in the naturals such that P of n is true for n greater than 1. It has to be something bigger than what I showed in the very first step. So assume it's true there. And now we have to verify P of n plus 1. So let's write Pn plus 1. Pn plus 1 is a statement 1 plus 3 plus 5 plus up to 2. I'm going to include the 2n minus 1 and then do the 2n plus 1 minus 1. And what are we trying to say that that's going to be equal to? And n plus 1 squared, right?
Yeah.
If you're trying to follow along, this is on the bottom of page 101. So that is the statement we have to verify. Now you're actually going to start on the left-hand side and try and get to the right-hand side of that statement. So let's look at it. 1 plus 3 plus 5 plus 2n minus 1 plus, simplify this 2n plus 1 minus 1. What would that be? Arithmetic. What is 2n plus 1 minus 1? 2 times n plus 1 minus 1. I'm asking you to simplify that right there.
Oh.
It's hard to say the parentheses. 2n plus 1.
Yeah.
This is only arithmetic.
There's so many parentheses there.
Yeah, it's hard to tell. Now, watch very carefully. This part right here, I know what that's equal to from my assumption step. I know that Pn is true. What is the statement for Pn? Oh, I took it away. Did you guys see that? Let me write it again. So that's the statement that I'm going to plug in for this part right here. We're assuming that one's true. So we're going to plug it in. So that's going to be equal to n squared plus 2n plus 1 by the assumption step. If you don't use your assumption step, you either did something wrong or you don't need induction. So you always have to use your assumption step. Now factor this for me. N squared plus 2n plus 1. What is that equal to? N plus 1 squared. So that means you got to that other side of the statement you're trying to show. Thus, Pn plus 1 is true. Now the final step, and so by induction, actually we can say PMI is shorter than typing induction. By PMI, P of n is true for all n in the naturals. There's our induction argument. I want to see it typed up that way. I want to see you identify what your P of n statement is. I want you to see referencing that P of n statement. It'll keep things a little bit straighter in your mind about what you're trying to prove. Yeah, when it starts saying prove.
Will we prove it that way for all of them?
Except your arithmetic will be different depending on which problem it is. So let's look at this one. This one was on the bottom of page 104. It says prove that for all n in the naturals. What does this capital pi mean? Big pi? So that's equal to, you're multiplying them together. When I is 1, you're going to have 4 times 1 minus 2 times when I is 2, it's going to be 4 times 2 minus 2 times all the way out to when I is n. So that means multiply. I suspected you guys wouldn't understand this one. That's why we're doing it in class. So what is our statement going to be? Let P of n, this is our hypothesis.
The pi symbol means multiply.
Pi symbol means multiply, yes. I equals 1 to n. 4i minus 2 is equal to 2n quantity factorial over n factorial. So that's our statement, that's our hypothesis.
We're trying to prove that the n is lower than natural.
You know, you assume that it's a natural number.
So what are we trying to?
You're trying to prove this formula for every natural number n.
But if we write it like,
I'm not assuming that it's correct. I'm saying let P of n be that statement.
so we're not writing it.
This is a hypothesis. For each n in the naturals if you want. That's our hypothesis. Then we have to verify for the first one. Now, what is P of 1? Let's go ahead and write it out. That means it's going to be pi, I equals 1 to 1 of 4i minus 2 equals 2 times 1 quantity factorial over 1 factorial. Simplify this, and what do you get? If you go from 1 to 1, that's just writing the statement down, plugging in 1 for I. So you get 4 times 1 minus 2. If you simplify the other side, you get a 2 factorial over a 1 factorial. What is 4 times 1 minus 2? What is 2 factorial? What is 1 factorial? 1. So P of 1 is true. Notice that I've lined the equations up, I've centered them, and I used a little arrow to get from the first line down to the next lines. If you're using multiple lines in a proof, you need that little arrow unless you're leading with an equal sign. What's the next step after showing P of 1 is true? You do an assumption step, right? So
That's the same as inductive.
the assumption step is assume that, so we would write this as assume there exists an n in the naturals, n bigger than 1, such that P of n is true. That's your assumption step. And then you have to show P of n plus 1 is true. No, this is, your first step is verify P of 1. That's the first step. The second step is the assumption step. The third step is to show that, and then this actually ends up being our fourth step is conclude.
The third step is P of n plus 1.
Yes. So I'm at this step right here. I have to assume there exists an n in the natural such that P of n is true. Okay, so I'm going to write it down. Assume there exists an n in the naturals bigger than 1 because we showed that P of 1 is true, such that P of n, and I'm going to write this statement down. So assume that that statement is true. What's your next step? Yeah. We must show Pn plus 1 is true. Yeah, show Pn plus 1 is true. So let's actually write down what Pn plus 1 is. Pn plus 1 is a statement pi, I equals 1 to n plus 1, 4i minus 2 is equal to 2n plus 1 factorial over n plus 1 factorial. So I have to show that. Now you're going to start on the left-hand side of your equation and get to the right-hand side of your equation. So let me go get some more paper. So let's write it down. If I center this, I'm going to center it starting on the next page. If I write this out, this is going to be 4 times 1 minus 2 times 4 times 2 minus 2, all the way out to 4 times n minus 2 times 4 times n plus 1 minus 2. You always include where the previous one would have ended for your assumption step. So all of these right here then become, and I'm going to write it this way so that you can see the assumption step. But according to the assumption step, what is this first part here equal to? And then I'm going to simplify this. You get 4n. plus 4 minus 2 gives you a plus 2. Now, at this point, we're a little lost. We don't know where to go. We are trying to get to this side right here, right?
Don't we just plug in N plus 1 for every N equals
Well, I have to get from this step right down here, this whole step to that side right there. How do you go from here to here? If we don't see that immediately, we just start playing with the other side.
As I say, because it's 2N plus 1 factorial is greater than.
Okay, so you want to, don't do inequalities. We have to have it equal. But factor out a 2 right here, and you have an n plus 1 there, right? That's a 2 times an n plus 1. Can you get from,
Is it supposed to be an equal sign on in this?
not right here.
Okay. So
That-
then just multiply that.
Yeah, I'm actually going to, yeah, put this over 1. And then notice that that becomes a 2 times an n plus 1 factorial. It's not quite right because I need an n plus 1 factorial. I'm missing something to be able to make it a 2 times an n plus 1 factorial. This is a 2n factorial. If I'm looking at 2, this is a 2n plus 2. Okay, I'll put it there. Yeah, from here, I just factored 2. What?
If you factor out the 2 from 4N plus 2, would be a 2N.
Oh, yeah. I'm missing that. Yeah, so it doesn't move it across. So what let's do is start working with the other side over there and simplify the other side. So let's look at our, what is that? I'm going to center these two. 2n plus 1 factorial over an n plus 1 factorial. That becomes a 2n plus 2 factorial over an n plus 1 factorial. So that becomes a 2n plus 2 times a 2n plus 1 times a 2n factorial all over n plus 1 times an n factorial. Are we good so far? What is an n plus 1 factorial? It's n plus 1 times n minus 1.
I know, but I'm how do you get from N factorial to N plus 1 factorial?
How did I go from here to here?
No, from the third, like, you
Uh-uh.
get this, yeah, from that.
I started a whole new line, and I'm dealing with this side of the equation now. Mhm. So I'm simplifying this, but what is that going to be equal to? Can you factor a 2 out from this one right here? So now this n plus 1 and that n plus 1 are going to cancel. Multiply this one through that one, and you get a 4n plus 2 times a 2n factorial over an n factorial, which is the same thing as we had, and I'm just going to leave this line off. And so I'm going to call this equation 1 right here, And I'm going to call this equation 2. And now we're going to get our conclusion. By 1 and 2, I know that Pn plus 1 is true because they're both equal in the middle. So Pn plus 1 is true. Thus, by PMI, I know that P of n is true for all n. And we're done with that. Do you guys see the steps to induction? They're the same steps over and over again. Your arithmetic is different, but your approach to it is the same. You guys get to try one.
So basically, because of the equation 1 equals
Because if equation 1 equals equation 2, then we're saying the left-hand side of Pn plus 1 is the same as the right-hand side of Pn plus 1. I made it go away already. See, this started out on the right, on the left-hand side. We got it simplified down. This is left-hand side, simplifies down to here. And now this is the right-hand side, and it simplifies down to here. If those two are the same, then the left-hand side equals the right-hand side. So you guys get to try some. We have an odd number of people, so a group of 3 and a group of 2. And choose one of them. You guys want to do the first one?
Can you please one of the
So first of all, write down what you're trying to prove. So this is Preston, and Preston, are you working with Sarah Lynn and Amanda? And then this is Corday and Joey. Can I disappear it back to one of the examples now? As you notice, they don't all fit on one page.
which proof should we use?
We're using this one.
Induction. You have to do induction.
But, I mean, there are 2.
The one, how you had it on the slideshow, it's not in the book like that, right? That one?
Oh, yeah.
That's not in the book, right?
This is a method that it is, but they didn't word it that way.
Well, like, I don't think they show the 2A and B stat.
They do on all of them. They just don't call it that.
So
They
is that what
hide
they
it
were
very well.
calling the inductive stuff?
The inductive stuff, yes.
But they never did the, I guess they just used.
Yeah. They use n and n plus 1 on most of the examples. So if you were looking on page 104 in the example on the bottom of page 104 that I just did, they labeled them as I, 2I, and 3I. 2I is most of the work. The first I is your verification step.
So how do you know if you're showing if one is the element of, well, I guess in the book it's one is the element of S, or if you're showing that,
That's the
P of
same as
one.
P of 1.
so they're both the same?
That means the same thing. It's just it's easier to think about it if you call it P of 1.
So they're, because you would use these on the same time, I guess it says it's the same proof.
Mhm.
You're proving the same thing. So they're both the same.
They're the same. It's just I like writing it this way better. It makes more sense to me to write it this way. Of course, start out by stating what your P of n statement is.
Which proof should we use? This one or this one? Okay, alright,
They're
sorry.
both the same. So like for this one, we would say, let 4 of n minus 1 is divisible.
Let them be the statement, 4 to the n minus 1 is divisible by 3.
Yeah, that's fine.
So you're gonna say P of n colon and then copy the whole statement down and then verify.
So the first step is to show P of one is true.
What does it mean to be divisible by 3?
And then third is a K.
Okay, so you need to feel one.
Yeah.
Do you do P of 1 first, or do we define divisible by 3? I think divisible by 3 first.
Verify P of 1. Okay, so first of all, your statement P of n is,
Do you want us to write the division rule first, or do you want us to verify?
no, we're always gonna leave it this way. And so then to verify your P of 1, you have to look at what, you're gonna have 4 to the 1 minus 1. How do you verify this is true?
Then this K such that.
So then we
No,
evaluate.
evaluate. What is 4 to the 1 minus 1? It would be 3.
And 3 is divisible by 3. 3 is divisible by 3.
Yeah, so you're actually gonna write it out, you're gonna write this statement out, and then you can say 4 to the 1 minus 1 equals 3, which is divisible by 3, then from P of 1 is true.
Oh, so we don't have to like write the division rule.
No, okay, no, you're just applying it.
Okay.
But when you get to your P of n, you're gonna actually do the division rule. So then when you say, assume P of n, then you can assume this, and then you apply your definition for divisible. So after you assume P of n is true, you apply the definition for divisible. So yes, you use your definition for divisible, but only at the assumption step. And then for your final step, you're actually going to use it again.
And the final step is like K plus 1.
Yeah, verify that P plus 1, P of n plus 1 is true, yeah.
So for the P of 1 part, we don't center that. Or do we?
Oh, we should have worked.
You-
That one you shouldn't need to center, only when you're doing a whole bunch of work, you start centering the pages. Unless the pages are so long that when you compile it, it hangs off the side of the page. Did you guys get your statement? Oh, yeah. So your statement is given as in P plus 5 equals 6 is divisible by 3. Over by 3 1. Did you do this on instead of assuming that P of n is 3 plus 1 over 9 You can that for your, for verifying P of n. Therefore, so you, therefore P of n plus 2. Because if you're going to P of n is one step, you're then going to go down to this step right here. But you're gonna have your polynomial here instead of theirs, your nq plus 5 n plus 6 plus whatever it is. You're gonna say, assume that is divisible by 3 for some n in the naturals.
Okay.
And then you have to verify your n plus 1 n is divisible by 3. And so then you have to look at your n plus 1 and you're gonna have to FOIL off with n plus 1. Okay.
So then we put it.
Yeah, that's what I was going to So, yeah.